So let's explore this idea a little further, that an adiabatic expansion of a gas will cool it down, and see if we can use that to get some useful cooling work out of a gas that we allow to expand. So let me draw a different picture of what it would look like if I did an adiabatic expansion. So if I've got a gas at some initial P1 and V1, I'm going to let it expand. So instead of drawing my piston vertically, what I'm going to do in this case is I'll put that gas in a box, and then I'll make a little pinhole exit in that box. So I've got a tiny little nozzle that the gas can expand out of. If out here the pressure is lower, then this gas will expand out into this external environment at the lower pressure. In fact, so the gas will expand out into this outer environment or outer container. If that outside pressure is lower, and if I insulate this box very well, then that expansion can be made to happen adiabatically, and the temperature of the gas will decrease. So I can use this adiabatically expanding gas to cool down whatever environment it's expanding into. There's two problems with that, however. One is that I'm allowing the gas to escape. I don't get to reuse it again. The other is, if the gas I've got is at let's say atmospheric pressure, then I need to find a vacuum, or I need to find a partially evacuated container to allow the gas to expand into, and that's not necessarily terribly convenient. What I'd rather do from a practical point of view is, again, let's say I have a gas at some initial P1 and V1. I want to have the outside gas, let's say, be at room temperature. So I want to be able to compress the gas that I'm going to allow to expand, and allow it to expand into a 1 atmosphere surroundings. So that's already a little bit more convenient. Let's say, so let me draw my container again with a little pinhole, a little nozzle that the gas is going to expand out of. In fact, let me connect these two containers by that nozzle. So I'm going to allow this gas to, at a pressure that's larger than atmospheric pressure, to expand into this container. But now I am going to imagine using a piston, because another inconvenience, at least computationally, calculationally, about this process is, as the gas expands, there's less of it in here, so the pressure keeps dropping as it does the expansion. But what if I use this piston and have an external pressure always pushing on this piston with a pressure P1? So a large external pressure pushing on this piston, forcing the gas through this nozzle. So you can think of this almost like a syringe. When you push down the plunger on a syringe, you would be squeezing, in this case, a gas, not a liquid, out the nozzle of the syringe and into what we can think of as perhaps another syringe or another piston. So this gas is constantly being held at an external pressure of P2 by the external pressure here. So initially, let's say, in fact, let me erase this and say initially the plunger on the second piston is all the way down. So when I push this plunger, the gas is forced through the constricting nozzle, and it's going to start to push the plunger of this piston back. As it goes, I can partially let part of the gas expand. This plunger gets pushed back a little bit. It remains at a pressure of P2. As I continue, pushing the plunger almost all the way down. So this gas ends up at a much larger volume than when it started, because the final pressure P2 is lower than that pressure P1, but I can forcibly compress this gas, pushing it through this nozzle, letting it expand into this lower pressure environment from this initial pressure and volume P1 and V1 to some final P2 and V2 once I've got all the gas into the second container or piston or syringe. So there's a sketch of a slightly more convenient way of compressing this gas and allowing it to do this expansion. If I wrap the whole thing in enough insulation, I can manage to do that in an adiabatic process. But now that I've constructed this more convenient process, it turns out it's not going to be as effective. because whereas before in the adiabatic expansion, the PV work, remember the gas does some work pushing back on the external pressure, so all of the energy required to do that work had to come from the internal energy of the gas. That's what did the cooling process. Now that I've constructed this process, it looks in hindsight like maybe that wasn't a good idea, because in this case, all of the PV work of doing the expansion into this second container is being paid for by the PV work of compression that I've had to do to compress the gas in the first place. And in fact, if we had an ideal gas, P1V1 would be equal to P2V2, and I wouldn't get any net cooling out of this process. But it turns out if you do this in the real world, you do get some cooling effect for a non-ideal, for a real gas. So we're going to be able to understand where that comes from. So let's think a little more about this specific process. So not the perfectly adiabatic expansion into a second container, but this sort of forced expansion with an external pressure P1 into a second container at a lower pressure P2. So I want to say, for that process, what do we know about, in fact, let's not use differentials, let's use delta.